Hello everyone. In this lecture we will discuss about the multiple gas phase reaction in polymath. In the previous lecture we have discussed about the problem 8-5. This problem 8-5, and it was about the multiple gas phase reaction. There were two reactions, A plus 2B give us C and 2A plus 3C give us D. The rate law for the two reactions were given to us, and the reaction were taking place in the PEG bed reactor, and it was isothermal reactor. The initial flow rate of component A and component B was given to us, which was 10 mole per minute. The volumetric flow rate of the fluid was 100 dm cube per minute, and the catalyst weight was given to us. The pressure drop in the PEG bed reactor was also given. The total concentration at the inlet was 0.2 mole per dm cube, and the rate constant of component A in reaction number 1 was given, and the rate constant of component C in the reaction number 2 was also given to us. This C is component is given is for component, and 2 is for the reaction number 2. So similarly, this A is component A, and this is the reaction number 1. So 1, 2 shows reaction number, and A and C shows the component. So there are two reactions, reaction number 1 and reaction number 2. Now the required was plot and analyze FA, FB, FC, FD, and the selectivity of component C with respect to component D in the PEG bed reactor. So the solution was, the first step was mole balance. So we apply mole balance on each and every component, which was component A, component B, component C, and component D. The mole balance for component A in the PEG bed reactor was dFA by dW is equal to RA dash. This is for component B, mole balance for component C, and this is mole balance for component D. The second step, we apply the net rate of component to each RA dash, RB dash, RC dash, and RD dash. So this is the net rate for component A, net rate for component B, net rate for component C, and net rate for component D from these two reactions. As the RA dash shows the R1A dash plus R2A dash, because A is present in reaction number 1 and also present in reaction number 2, but B is present only in reaction number 1. Similarly, C is present in reaction number 1 and reaction number 2. So these two are for C. Similarly, D is present in reaction number 2 only. Then we apply the rate law. These rate law were given to us in the problem. Then the relative rate for component in the reactions were, these were the relative rates for component in the two reactions. The relative rate, then we relates the relative rates, and we obtained these type of reaction. And the net rate for the species A, species B, species C, and species D were given to us. That was the net rate A, B, C, and D. Then we put equation number 5, 6, and 7, 5, 6, 7, and 8 into equation 1, equation 2, equation 3, and equation number 4. So equation 5, 6, 7, and 8. The equation number 5, 6, 7, and 8 were equation 5, 6, 7, and 8. Equation 5. This is the equation number 5, 6, 7, and 8. We put these equation in these equation number, these equation 1, 2, 3, and 4, which were the mole balance for component A, B, C, and D. So we obtained these type of relation when we combine the mole balance and net rate of component A, B, C, and D. Then we know that the selectivity of component C with respect to component D in the flow reactor, which is PEG bed reactor, mole flow rate of component C divided by mole flow rate of component D. Then after that, after the combination of mole balance and net rate, we will go to step number 6, and in step number 6 we obtain a relationship between the concentration and the we obtain the relationship between the molar flow rate of component and concentration of component. So Ca is equal to this, the relationship between Ca and Fa is this one, and the relationship between CB and FB is obtained from this relation. Similarly, CC and CD. So we obtained these relation, and FT is the FA, FB, FC and FD. This is the total molar flow rate of component in the packed bed reactor. The parameter were given to us. This was the initial flow rate, initial composition of component A and component B. So the initial concentration was given to us, and this can be obtained from CT naught is equal to P naught divided by RT. So it can be obtained from this relation, and this is the volumetric flow rate is given to us 100 dm³ per minute. It is given to us K1A, and this is was given FT naught was 20 mole, because 10 mole per minute was for component A and 10 for component B. So it was 20 mole per minute. So when we combine the mole balance and net rate, we obtain this type of relation. When we combine equation number 1, 2, 3, 4 and 5, 6, 7 and 8, then we obtain this type of relation. Then we know that rate is equal to is a function of concentration. So from rate we write these relation, because the rate and concentration relation are given in the problem. Similarly, the R2A dash is equal to this one, so we write this one. Similarly, for component B, we combine the rate and concentration relationship. Similarly, for component C, and this was for component D. Now then we put in place of CA, we put this one. In place of CB, we put this relation. In place of CC, we in place of this CC, we put this relation. In place of CD, which is given in place of CD, we can put this relationship. So in place of CB, we can put this one. In place of CA, we can place this one. Similarly, in this one, in place of CA, we can put this one. In place of CB, we can write this one. In place of CA, we can write this one to the power 2. Similarly, CA square CC to the power cube, so we can place this one to the power cube in this place. So after putting the concentration value in these equation, this and this one, we will write 4 equation. So this equation shows the relationship between concentration and molar flow rate of component A in the packed bed reactor. So we put in place of concentration, we put this value for component CB, and for CA we put this one, and this is for the CA, this is for the CC, this is for CA, CB, and this is for the CA, CB, and this is CA and CC. So similarly, this is for the CA, and this is for the CC, and this is divided by 3, because there is this is a division by 3, so we divide it by 3. Then after that we form a differential equation between pressure and weight of catalyst, and this alpha value is given to us, pressure drop, its value is given in the problem, and this phi is capital phi. This is capital phi. Capital phi is equal to small phi divided by small phi naught. So small phi divided by small phi naught. So the small phi naught value is given to us 1 atmospheric. We assume at 1 atmospheric pressure. The initial value of catalyst was 0 in the packed bed reactor, and the final and the total weight of catalyst is given, which is 1000 kilogram. So now we are going to plot these equation, this one, this and this, in the POLYMATH. So we will go to POLYMATH. We will open POLYMATH. So this is POLYMATH. We will put the first differential equation. The first differential equation is between FA divided by dW. dW is equal to minus K1A into CT naught multiply by Fa divided by Ft multiply by P small phi divided by small phi naught and close the bracket. Similarly, N2 Ct naught multiply by Fb divided by Ft and multiply by small phi divided by small phi naught and close the bracket, and to the power 2 minus K2C and to Ct naught multiply by Fa divided by Ft multiply by small phi divided by small phi naught to the power 2 and to Ct naught multiply by Fc divided by Ft naught. So Fc divided by Ft multiply by small phi divided by small phi naught to the power 3. This was the first equation. So Fa naught, the initial value of Fa naught, the initial molar flow rate of component A to the packed bed reactor was 10. So it was 10 and click on done. So there are too many brackets, so okay, there are too many brackets, so we can unequal number of parentheses, too many brackets, so unequal number of parentheses, so it is phi divided by this one. Here we can write the parenthesis bracket. So now we can click on done. So this was the first equation. Similarly, we can put the equation number 2 for Fb divided by dw and equation number 3 for Fc divided by dw and equation number 4 for Fd divided by dw. So I am just putting it from another window. I am putting it from other window, from this window. I have already done it, so I am putting it just from other window. Fb divided by dw and this is Fc Fd. So I am putting it, I am copying it, and paste it. So I am copy and paste. Similarly, I am writing equation number 5, which is the relationship between pressure and weight of catalyst, because there is pressure drop in the packed bed reactor and the pressure drop value is given to us. So I am writing equation number 5. So equation number 5 is d phi divided by dw. So d phi divided by dw is equal to minus alpha. So I am writing A for alpha. So minus alpha and multiply by P naught multiply by P naught multiply by Ft multiply by P naught divided by 2 multiply by small phi and to Ft divided by Ft naught. So Ft, which is the total flow rate of all component at any time in the PBR, and Ft naught is the initial total molar flow rate of component A and B, which are entering to the packed bed reactor. So and P naught, the P naught value is 1. Suppose it is 1. So the P naught value is 1. I am writing it. Click on it. Click on done. So click on this one. So these are the 5 equation. Now there are undefined variable K1A. So K1A, the K1A value is given to us. It is equal to K1A value is given to us, and it is 100. It is 100. Oof. Similarly, the K2C value is unknown, so K2C is equal to, the K2C value is 1500, which is given to us. 1500. Now there are A value, this is A, Ft naught, these value are unknown to us, so the A value is equal to pressure drop, alpha is alpha, and alpha is equal to 0.0019. So 0.0019. Similarly, the phi naught value is unknown, so the small phi naught is 1. So it is 1. The Ft naught, now what is Ft naught? The initial total molar flow rate of component A and component B. So there are two components initially, A and B, and the molar flow rate of the two components are 10. So 10 plus 10, which is 20 mole per minute. So it is 20, and now Ct naught, the Ct naught value is given to us, which is 0.2. Ct naught, the initial composition was 0.2. Don't write the unit of concentration, pressure, or other flow rate in this interface, only write the numbers. So now Ft is equal to Fa plus Fa, Fv, Fc, Fd. Now initial and final value of the independent variable is not set. So what is independent variable? The weight of catalyst is independent variable in these differential equation. As you can see, df by dw, this is independent variable, this is independent variable, this is independent variable, and these fa, fb, fc, fd, dp, these are the dependent variables. So we can go to this, define the initial and final value of independent variable, click on it. The initial value of the weight of catalyst is 0, click on OK. The final value, the total weight of catalyst is 1000 kilograms, so click on it. So these are the initial and final value. It will take some time, so this is the final. Now click on table, we can draw graph, table and report. So now go to the purple to solve, or you can export from Excel. So I'm clicking on it to solve. So click on it. So it will take some time to solve. This is the POLYMATH report. This is the alpha, C naught, FA, B. These are the initial value, minimal, maximum value, final value. These are the differential equation which I have. So these are the differential equation. This is the explicit equation. These are the general. So you can go to the graph. These are the graph, and this is the FA, FB, FC, FD and P. So these are the graph. So this is FA, FB. Now I am writing another equation also in this POLYMATH. So this POLYMATH. So this one. So I'm there was another for the selectivity, we can write SCD. Selectivity of component C with respect to component D is equal to if W is greater than 0.0001, then give us FD, if C divided by FD, else give us 0. So now I am solving it. This is for selectivity. This equation is for selectivity, because selectivity is equal to FC divided by FD. But if I am writing FD in this place, then the selectivity, then the selectivity of component C with respect to component D will go to infinity, and it will crash our POLYMATH. So I am writing very small value of the weight of catalyst. So if the weight of catalyst is greater than this number, then FC and FD and selectivity value will be given to us by POLYMATH. Otherwise, if the weight of catalyst is less than this number, then it will not give us a selectivity value, it will give us infinity and it will crash POLYMATH. So I am writing this if and else equation. So if W is greater than this number, then it will give us selectivity, FC divided by FD. Otherwise, it will give us 0 value. So I am solving it. Click on this number. So it will take some time. This is the calculated. I have already discussed this one. And POLYMATH report. Come to the graphs. So this is the graph between FA, B, FC, FD and P with respect to weight of catalyst W. So click on it. XY value. So I am changing the X and Y. This. So this is the grid line, if you are interested, but I am not interested. This. So this is the XY, the font size, scale and margin. These are the curve, draw marker. You can also, it is very good. So now you can border width can be decreased. Now I am closing it. Now this, from this graph, it shows that the flow rate of component A, this is initial flow rate of component is 10, initial flow rate of component B is also 10 mole per minute, and the A and B is decreases with the passage of time in the packed bed reactor. Similarly, Bs also decreases with the passage of time in the packed bed reactor. But if you see the component C and component D, C and D, so the component C, this is for the component C, the C values increases because C is producing in the packed bed reactor and D is also producing in the packed bed reactor, and this is for the pressure drop. So the initial pressure was 1, but it is slowly and gradually it is decreasing inside the packed bed reactor. You can see it is about 0.2 or 0.3 atmospheric pressure. So it is slowly and gradually decreases inside the packed bed reactor because this is the pressure drop problem in packed bed reactor. So you can see this is the graph. Now you can go to, this is the table, you can design, you can, this is the draw marker. I also, this is the weight of catalyst. So click on it, I am double click on it. So the weight of catalyst is in kilogram, so in kilogram kg. So click on OK. So the weight of catalyst occur in kilogram. Now you can go to the table. This is the table, FA, BFC, FD, and this is the weight of catalyst. You can go to the table. Similarly, this is the design. So this is the curve, the X. So title, I can also write title, relationship between flow rate versus weight of PBR. PBR mean packed bed reactor. So relationship flow rate, you can also write relationship between flow rate and pressure with respect to weight of catalyst. So I am closing it, close it. This is appear here. Now the curves. So I am now, in order to draw the relationship between selectivity and the weight of catalyst, so I will unmark it, FA, FB, FC and FD, and phi also. So these you can selectivity, this one, selectivity of component C with respect to component D. Click on it and close it. Now you can see that this is the weight of catalyst and this is the selectivity. So you can see that the selectivity is very high at about, when the weight of catalyst is 40 or 50 kilogram, then selectivity is very high. So when the weight of catalyst is very small or at the beginning, the selectivity of component C is very high with respect to component D. So we can use the 60 or 50 kilogram weight in the packed bed reactor to increase the conversion of A and B to produce more and more C as compared to component D. After 60 or 70 kilogram weight of catalyst, the selectivity decreases to 0. So you can also draw the graph between selectivity and weight of catalyst. So this was just a problem related to the multiple gas phase reaction in PBR. Thank you very much for your attention. If you are new to my channel, please like and subscribe. Thank you very much.